Vinda, can you go get the blinds of that? Hello, everybody. I see that 11 of you are here. Welcome to review session for quiz 5. Today we'll be going over learning objectives 2.7, 2.10 through 2.20. And those are primarily separation techniques, intermolecular forces, and a little bit about the macro the macro properties that result from these intermolecular forces. So let's start with a quick review of concepts. Then I will take your numerical problem from the blue packet. Then I'm going to go over the practice quiz. All right, welcome to the daylight savings time. I bet you guys all enjoyed sleeping in. And let's get started. All right, so separation techniques. Why we need to study separation techniques is because a lot of the material that chemistry uses is used for commercial purposes. And a lot of the substances that are found in nature, they are found in an impure state. So we need to be able to separate them. And when we separate, mixtures can be separated rather easily through physical means. But if it is a compound like H2O, then you need to really break the bonds, intramolecular bonds apart using chemical methods. So when it is an easy separation, that means you are only overcoming intermolecular forces. So there are very many separation techniques that we talked about. So the first one was hand separation, and all of you have used it to pick out your favorite or least favorite vegetables from pasta, or to pick out your favorite kind of Skittles or M&Ms. And what is needed for hand separation is visible differences, because our eye need to be able to see it. And they should be either in color or shape or texture. And then we use a very special tool, our hand, to separate it. So that is hand separation. Then there is filtration. Filtration is when you have different size particles. So this is typically done for precipitates and solution to separate out precipitate. And this is for heterogeneous mixtures. Typically, we are looking to separate precipitate using this technique. In filtration, you use a very special sieve, which is our filter paper. And the filter paper has very teeny tiny holes that you cannot see. And when you pour a precipitate in here, precipitate stays on the top. And what comes down is called the filtrate. So filtrate has small little teeny particles that can pass through the filter paper, and what gets left behind is precipitate. We often use filtration in chemistry, especially when you're trying to separate a solid from a mixture of solution. And in this case, when you are quantitatively interested in the amount of precipitate, you must weigh your filter paper before you put the precipitate on that. So that's filtration. And the next technique is using separatory funnel. And you saw the use of this in Quick Cake Relief Lab. This is separatory funnel is used for separating immiscible liquids. And this is a fancy term for the liquids that do not mix with each other. So a separatory funnel is a funnel, and you put the two immiscible liquids in there, one, and then two. And the lighter or less dense liquid will be on top, and the heavier or more dense liquid will be at the bottom. And if there is a component of a mixture that is more soluble in one or the other liquid, it will go in that. And when you take out that layer, that component of the mixture comes out with that layer, and you can evaporate the liquid and get that component. So that is using separatory funnel. Then the next method, hand separation filtration using a separatory funnel. This is called centrifugation. And centrifugation is like using, this is a method that uses differences in mass. Okay, so as you spin something in a circle, the heavier particles settle at the bottom, followed by smaller and followed by smallest particles. And then you can separate out each layer by adding different solvents and dissolving one layer carefully, then second layer and third layer, and then evaporating the solvent. And the last method is chromatography. And chromatography is a method that is used for separating a mixture of inks. And in this, you have a stationary phase and you have a mobile phase. So stationary phase could be paper, could be column. I don't think that's visible. Could be paper, could be column or gel, or could be gas. And based upon that, we call it gel chromatography or paper chromatography or gas chromatography, depending what our stationary phase is. Then we use a solvent, which is mobile phase, which travels on the stationary phase. And this methodology is used for homogeneous mixtures of, generally it is used for ink, but this has application in lots of things, from the urine strips to pregnancy tests to very many other things are used for chromatography. And the idea here is one or the other component in the mixture has more affinity towards either the stationary or the mobile phase. And this greater affinity is because of the intermolecular forces and the concept like dissolves like. So if your stationary phase is polar, then the polar component of the mixture will be more attracted to it. If your mixture is more attracted to the mobile phase, then it will travel more with that. And we did a formative assessment on it where we had some water and we had a strip and we put our mixture there, make sure the spot is above the water so water travels up. And as the water travels up, different components separate based upon their liking for the stationary or mobile phase. And the last method here is distillation. And I can write it over here because this part is still available. Distillation also can separate a mixture, homogeneous or heterogeneous, as long as there is a difference in boiling points. And distillation is used a lot in distilleries which make alcohols because it can separate out the unwanted alcohols like methanol from the wanted alcohols like ethanol. And this technique, you take a distillation flask and you take your mixture of two components. Let's say the blue one is lower boiling point and the black one is higher boiling point. So what's going to happen? You heat up this mixture, and then as the temperature starts to rise, the first boiling substance, which is the blue one in this case, will start going through this tube, and then you cool this vapor in this tube by circulating water through it. Water goes in through here and water comes out through here. You push water from down so that it circulates through the whole jacket and the water comes out from the top. And then because it is cooled, the vapor is cooled here, Now this gets collected and condensed and collected. So this is the lower boiling point substance that gets collected first. And then you remove this and you have a thermometer in here to tell you what's the temperature like. Remember, at boiling point, the temperature does not change. So you have things, as long as the temperature is not changing, you know you have the same component here. And the temperature starts rising again. And when the temperature stops rising, you know, now you're boiling the higher boiling point component. And then you remove this flask and put a new flask in there, and you can collect your second one. What is very important in separation technique is to be able to write all of these at particulate level drawing. So in particulate level drawing, sometimes it may be confusing. You got to look through carefully as to what is happening. In fact, one of the questions in your blue packet was confusing to some of you because it showed charging the column and was a little fuzzy, and I'll address it when I go over the problems. But your focus in the separation techniques is in understanding what type of substance can that technique be used in. Also, what does it look like at particulate level? So really think through at the micro level when you're talking separation techniques. So that is separation techniques 101. Now I'm quickly going to go over different types of intermolecular forces, and then I'll address your questions. Okay, all right, intermolecular forces. IMFs are intermolecular forces. So you know that chemical bonding or intramolecular forces, as we know them, are ionic, covalent, covalent network, metallic. In covalently bonded molecules, there are also interactions between molecules that are different from interaction within molecules. We call them intermolecular bonds. In rest other, like ionic, covalent network, and metallic, inter and intramolecular are one and the same force. So when we talk about IMFs, we are talking ion, which really is ionic bond, right? We are talking ion dipole. We are talking hydrogen bonding. We are talking about dipole, and we are talking about London dispersion forces. So these are what's happening at the micro level, and then we'll talk about its macro impact. So what properties are impacted by this? Let me take a minute and go close the blinds because I think there's a lot of shadow from there. Okay, all right, let's do this. So ion or ionic bonds exist between any ionic compounds in solid form. So if you have Na plus and Cl minus, and you have Na plus, opposites attract, Cl minus, and then Na plus here, and Na plus here, and Cl minus here. Notice that the anions are larger than cations. Then the attraction between these oppositely charged Na plus and Cl minus, all of these are called ion-ion attractions or ionic bonds. Now, how do you determine the strength of ionic bond? You can determine the strength of ionic bond is determined by Coulomb's law. You remember, anytime there's charged particles, the law that governs the attraction between them or repulsion is Coulomb's law, where the force of attraction or repulsion is directly proportional to the charges between them and inversely proportional to the square of the distance between them. So what it means, if you compare the ion-ion interactions between KCl versus NaCl, they both have Cl common in them. They all are +1 and -1 charge. The difference between them is K is a larger radius, K plus, than Na plus, right, which is smaller radius. So consequently, the force of attraction will be higher in NaCl as compared to KCl. So that is ion-ion interaction, and it is fairly strong. If we had to predict the strength of these attraction, ion-ion is greater, followed by ion-dipole, followed by hydrogen, followed by dipole-dipole, and London dispersion forces are the weakest one. However, this is prediction. It could be that a London dispersion force is stronger than ion dipole or dipole-dipole if it is the strongest London dispersion force compared with the weakest of dipole-dipole. So that they will ask you to justify given upon data. But if you are asked to predict, then you follow this pattern. Now, ion dipole is for ionic compounds, but in aqueous solution. So anytime you take an ionic compound, NaCl, KCl, K2SO4, and make aqueous solution of it, we call it as ion dipole. Because what happens if you were to add water to NaCl, then Na plus and Cl minus are separated by our very own water molecules that orient themselves around Na plus with oxygen and facing the Na plus, opposites attract, and Cl minus, the hydrogen end, facing the Cl minus, opposites attract. And here, this interaction, guys, this, all of this, and this, and this, that is called ion dipole. And ion dipole interaction strength is again determined by Coulomb's law. And the larger the ion, the lesser is the ion dipole attraction. Because water molecule is the same, right? If it is a smaller ion, then there will be greater attraction. Or larger the charge, there will be greater attraction. Now talking about hydrogen bonding. Hydrogen bonding is a special type of bonding when hydrogen is covalently bonded to N, O, or F. Remember, hydrogen is fond of phon, okay? Then the intermolecular bond is called as hydrogen bond. To explain this more, if you have hydrogen bonded to fluorine, then this will be a dipole because the electronegativity difference between them is between 0.3 and 1.7. But this end becomes positive, this end becomes negative. I put delta for very small charge. And this attraction between them, fluorine and hydrogen, this is hydrogen bond. This, not hydrogen bond. That bond is covalent bond. So hydrogen bonding exists in HF, ammonia, and H2O. okay, or any other place where hydrogen is directly bonded to NO or F. Now, dipole, this exists in polar covalent molecules. And how you know polar covalent molecules? When electronegativity difference is between 0.3 and 1.7, then we know it is a polar covalent molecule. And in that case, like if you have HCl and HCl, this is polar covalent bond. This bond is polar covalent. This covalent bond is polar covalent. So it gets polarity. This end is positive, this end is negative. And then the attraction between these opposite ends is called as dipole-dipole. Note, this is permanent polarity, right? It's not like it's coming and going. A polar molecule is always a polar molecule. So this is called permanent dipole. Then there are LDFs, and LDFs are temporary dipoles, meaning this dipole is generated temporarily due to the motion or movement of electron cloud, but it doesn't stay. That's why these are the weakest forces, and they exist in all compounds, but where they become significant is if nothing else is present, only this is present, that's when they become significant. So they are significant in non-polar compounds and noble gases, because there's no other bonds in noble gases. Okay, so non-polar compounds, you can think of it when you have like H2, N2, Cl2. When two of the same atoms are bonded to each other, noble gases are helium, neon. When they are by themselves, then this is London dispersion forces. And how they come about is when there is, let's say this is neon and this is electron cloud, a chance could be that all of the electrons move to one side or most of the electron. So that side acquires a little negative, other side acquires a little positive charge. It causes the same phenomena in the neighboring atom with a little negative charge on one end, little positive on the other end. And then the attraction between them is called LDFs. And as soon as the electron cloud comes back to its original distribution, then London dispersion force will disappear. But this phenomena then may be happening in other molecules or atoms as well. One other thing you must remember here the strength of LDFs increase with increased molar mass because there can be bigger electron distortion, electron cloud distortion, right? And that is a summary of all of the intermolecular forces. Now I would like to move on to the practice problems, and I welcome your questions, but I see a few comments, so let me take those. Hey Dan, do we ever see ion dipole outside of aqueous solutions? I haven't, but in chemistry I hesitate to say never. So generally it is for aqueous solution where you see ion dipole. Sunny, do we have to memorize 0.3 to 1.7? No. There will be two things, Sunny. A, you can ask for the exact values. If they are very close right next to each other on the periodic table, then I can give you electronegativity. But if they are far apart, you remember across a period electronegativity increases and down a group electronegativity decreases. If you can, based upon the trend, can tell this is higher electronegativity, this is lower, then that's fine. Then I will not provide you that. But if they are close enough for you not to ascertain, then I'll be happy to give you the values so you don't have to memorize any. ethane. How do you compare London dispersion forces of large molecule? Well, ethane, the only criteria here is you're looking at the ability for electron cloud distortion, which comes from larger molar mass or more electrons. So that is one criteria there. If it is a single atom, if it is a molecule, then in addition to molar mass, another factor that comes into play is the shape of the molecule. If it is a linear chain where the electrons can distort more, then linear chains tend to have greater polarizability. If it is a branch chain and a more condensed molecule, it'll have lesser polarizability. Typically, you will not be asked to choose between one or the other. It'll be given to you. But I know there was a question where you had to do one or the other, and it'll be pretty clear cut. And I'll be happy to address it in the problems if this is not good enough, Ethan. Stephen is no. NaCl, Stephen, is considered ionic because remember, there is a metal cation in there. Anytime you have a metal cation bonded to anything, any negatively charged, either monatomic or polyatomic ion, it is polar. Non-polar cannot have metal cation in them. So polar or non-polar cannot have metal cation. So NaCl is ionic. Jocelyn, are ionic bonds and ion-ion interchangeable? Ionic bond is the type of bond. Ion-ion is the type of interaction between them. So yes, I don't know if you really use them interchangeably. If a bond is asked, what is the bond? Then you'll say ionic bond. You don't say ion-ion bond. You say ion-ion interaction. So slight difference. Shravya, pretend there is a molecule like BEH. Will there be a hydrogen bond between BEH and HF? HF, so HF definitely, and on the other side, so Shravya, knowing what I know about chemistry, BEH does not bring enough polarization, but I think your question is, if it is HF and you have not a HF, but another electronegative atom or a molecule on the other end, would that still be hydrogen bond? Answer is yes, it'll still be hydrogen bond. So both molecules don't have to be HF. Alan, for HOH, which bond is the hydrogen? Other one, dipole. Yes, for HOH, let me erase this now so I can answer your questions with pictures. So in HOH, right? So this is one molecule, this is other, these, the black ones, right? These are polar covalent bonds. And because of that, what happens is this hydrogen acquires a positive charge and the O side acquires a little negative and hydrogen is little positive. So between H and the O, this one is hydrogen bond, Alan. So Stephen, yes, it has to be Na+1 and Cl-1 for making it a neutral formula unit. NaCl is not a molecule. It is a formula unit because this is an ionic compound. It is not a molecule. Molecules are covalent compounds. Alrighty. Any other concept questions at this point? What would be an example of a mobile phase? So mobile phase, when we did our paper chromatography, the mobile phase in there was water and stationary phase was paper. Any other questions, guys, on concepts? In chromatography, how can you tell in a particulate level? So Karina, in chromatography, in particulate level drawing, you will see some kind of representation for a stationary phase. It could be something like that, right? And some kind of representation, maybe they will decide not to show stationary phase or show stationary phase. Then they may show a cluster of red molecules maybe stuck towards the top, and then they may show some other molecules moved more towards the bottom, right? And now you know, and then they may decide to show mobile phase or not. So as long as they are separating different kind of molecules along a stationary or a mobile phase, they may decide to show you stationary phase or they may decide to show you mobile phase. So you can tell by cluster separation of different molecule along with a stationary or a mobile phase. They will tell you something more because just drawing this will be hard. There will be a little bit more that will tell you that this is chromatography. You're welcome, guys. Okay, so next thing I'd like to move on to is your blue packet or the practice problems. And my bad, guys, I forgot to put your key up for quiz 5. So I put it online this morning. That's when I got on the Facebook group and realized that I had forgotten to do that. So I hope you got a chance to look over the key. But I am taking questions from the blue packet, our practice problems from Unit 5. Any questions on this packet or this packet? You'll have the blue version of it. Welcome, Karina. Oh, there goes my dog. Okay. Number 15. Number 15, and this was a pretty confusing drawing, and this is where it had a lot of noise. And the signal was not that clear. So you kind of have to see on the top here, what you can see is circles here, right? Maybe I should use a thinner pen. So you can see some kind of circles here, right? With some smaller circles and positive charge. So because you don't understand gel chromatography very much, you won't be able to know that what is happening is you are charging the gel, because if there is no charge on the stationary phase, then all of the particle will just pass through it. So you want to create a charge. It is called charging the gel. That's what is shown here. This one here is showing you the mixture. So you have triangles and you have squares in your mixture. This is just the solvent that is charging it is coming out. And then you see that the triangles come out first. And then you see that the rectangles are coming out. And after that, it is recharging or cleaning out the column. So that's what it is showing. So basically, to your interest is this one where you see there is a mixture. And then you see that the triangles coming out first. and then you see the rectangles are coming out later. So really what you get from this picture is the triangles have more affinity for the mobile phase because it is moving out first. And squares have less affinity for the mobile phase because it is moving out later. So that's why it says, look at the particulate level diagram for chromatography, given that the solvent was non-polar. So they are specifying that the mobile phase was non-polar. Then a student makes a claim that triangles are more non-polar than squares, right? Do you agree with this claim? Yes, because the triangles moved out first, meaning they had more affinity for the mobile phase. Because mobile phase is nonpolar, hence the triangle should be nonpolar as well. Alan, can you ask one of your friends to send you a picture of the copy of the practice quiz? If you can get one of your friends to do it, I'll be happy to. Send me an email and I'll respond to that. Any other questions on the blue packet? So Stephen's question, how do covalent network bonds compare to the bonds you showed in ion? Very good question, Stephen. So covalent network like SiO2. What happens in SiO2? Si is combined with two O's, and those O's are combined with other Si's all through covalent bond. Right? So there is every single one of the bonds. Inter or intramolecular is a covalent bond in a covalent network solid. So every single bond, inter and intra, are all covalent bond. And this is how covalent network differ from ionic or ion dipole, any other, because every single bond in a covalent network compound is a covalent bond. Okay, Alan, so send me an email and I'll attach the link for you to print. So you can print out the pictures, Alan, of the quiz? Number 4 and 5 in the blue packet for Shravya. Butane, chloroethane, acetone, and 1-propanol all have approximately the same molar masses. Data on their boiling points and solubilities in water are listed in the table below. So this table here in question number 4, this table shows butane, and then it gives its structure of straight carbon chain, and its boiling point is 0. And what? 0 degrees Celsius? Yeah, that's what it boils very, very low. Then there is chloroethane, which is CCCl, and it is 12. Then there is acetone, CH3O, CH3. I'm not filling hydrogens here, you know, for each carbon there should be 4 valencies. So whatever is not filled by the main bonds filled by hydrogen. And this is 56. And then you have 1-propanol, and that is CH3, CH2, CH2, OH, and this is 97. And they say, explain the difference in boiling points of butane and chloroethane. So here to here, you know, chloroethane is higher boiling point than butane. And the reason is there are only LDFs here, but this one will have dipole due to CCl bonds polarity. because dipole-dipole are stronger than LDFs, hence it'll have a higher boiling point. Part B says boiling points of acetone and propanol, these two. Why is there a difference between them? Now they are both polar, right? This CO bond is polar and this OH is polar, but this one is bonded through hydrogen bond. This is a special kind of polarity, which is hydrogen bond, and this is only dipole-dipole. Hence, because the hydrogen bonds are stronger, that's why propanol's boiling point is much higher than the other one. So that was number 4 for Stravia. Number 5 says you have H2, C3, H8, and HF. And this is negative 259, that's the boiling points, negative 190, and HF is negative 92. Remember, negative 92 is highest boiling point, and this one is lowest boiling point. And if you look at it, which makes sense, this is hydrogen bonded. Both of these are LDFs, but this is a longer chain compound. Hence, its boiling point is much higher than hydrogen, which is just a very small molecule, very less electron cloud distortion, and less London dispersion forces. Stravia, did you get it? So then on to Stephen's question, how does the strength of the covalent network compare? It is covalent bonds. Covalent bonds are the strongest. Out of any compounds, covalent network compounds have the highest boiling points, highest melting points. They are insoluble in anything. They're very stable compounds. They are hard because they're all connected through these covalent bonds that are rather rigid and inflexible. Sunny, number 23. Indicate the strongest attractive force that must be overcome in all of these, Sunny. So for number 23, you have Hg, vaporize Hg, okay, and melt NaNO3 or boil C3H7OH or dissolve CH3 twice CO. That's my daughter having a sneeze. We are both laughing away. I asked her to be quiet. Just a human moment. Okay. In H2O, as we are looking at which one is the strongest force to overcome, we need to think about what forces are present. In Hg, you know, this is an exception because mercury is a metal that exists in liquid form. You should know this. So here you will be overcoming a metallic bond. In NaNO3, you'll be overcoming ionic bond. In this one, you are overcoming hydrogen bond. Guys, note, you're not breaking covalent bond because you're not separating C3H7OH in its elements. You're just separating C3H7OH molecules. So you're breaking hydrogen bond. And in dissolving these, you are creating dipole, or you're creating hydrogen bond because water and the O on this can form hydrogen bonds. So which is the strongest bonds of the bonds given? Ionic bond. So that is why your answer will be NaNO3 for number 23. Number 13. So guys, I can go over the question. I think it'll be very helpful. If you don't understand the entire question, I can go over the entire question. But if you have a specific part of a question or a specific thing you don't get, then you can specify so it can go a little faster. Because I don't know if you don't get the entire question or there's a little part in it. And I understand, no problem. I'll do the entire question if you have question on the entire one. So in number 13, there is this table and in number 13, you have HF, you have HF who is 20 degrees, and HCl is negative 85, and HBr is negative 67, and you have HI as negative 35. So you see that this is very high. This is number 1. This is second highest, this is third highest, this is fourth highest. And if you look at HCl to HBr to HI, so this is very clear. This is hydrogen bond, right? Rest of these are dipole. So if you now know, you know they are all +1, -1, but you know that the radius of H to Cl, H to Br is still bigger, H to I is still bigger. So the distance is increasing. So if you go according to Coulomb's law, what will happen is, because the radius is, the internuclear distance is increasing, then the force of attraction should decrease, and HI actually should have the least out of these 3 boiling point. But that's not what the data is showing. So they are not looking for you to explain it using dipole-dipole. And that is why I say that the data will lead you to the question. So here, what is happening is they want you to address, if HI is the highest, you know this is the largest atom, I, out of the 3 halogens. So this will have the highest molar mass, greatest electron cloud distortion. So they want you to address LDFs here. So you will say that HI has the highest boiling point because I, being the largest atom, has the most distortion of electron cloud, resulting into highest London dispersion forces. So this could have been addressed either way. If they had given you HIs least, then they wanted you to look at the dipole-dipole. But because they gave you HI as the highest, you know you need to address it with London dispersion force. So that is 23, and that was 13, and then 25C. 25, I do not see a 25 here. 25 says, dry ice melts readily at room temperature. So dry ice is CO2, right? So this is, let's say, you don't know the structure, so I don't expect you to draw this right now, but that is the structure. Let's say it is CO2 and CO2, right? You know this bond is LDFs, and if you have to show it melting, so you can make them closer together, right, in a solid state, but when it is molten, then you can draw them a little farther apart. Okay, maybe break one of the London dispersion forces. This would be acceptable drawing for that. That is Sunny. Stephen, blue packet number 7. So number 7 and then 17. Which of the following is most soluble in water? And if you look at number 7, Stephen, you see the difference, and I'm showing you here. This is number 7. The difference in the molecules, they all have OH in them, right? Well, 3 out of 4 have OH in them. 1 has a CO bond in them, right? You know, CO is only dipole-dipole. The OH ones are hydrogen bonds. So now the question is, which of these will have the strongest hydrogen bond? The strongest hydrogen bond will be in the smallest molecule, because the carbon chains come in the way of forming that hydrogen bond. Think about if there are large molecules trying to orient themselves so that they can attract, it's going to be harder. If there were smaller molecule that are moving and trying to orient themselves to form that bond, then that is easier. That is why CH3OH will be most soluble in water, because water molecules can have easier access due to the compact nature of molecule to form that hydrogen bond. Number 17. Which of the following processes are covalent bonds broken? So in all of these, remember when you melt benzene, let's say benzene is C6H6, right? So there are 6 carbons. Benzene structure, well guys, is like a ring. So I can draw it, it's wrong. And when you put this, means all the bonds are taken care of. There are 6 carbons and 6 hydrogens around it. When you boil benzene, you are just breaking the London dispersion forces between them. You are not breaking covalent bond. When you melting quartz, silica, SiO2, remember this is a covalent network bond. And now you're breaking a covalent bond. When you boil C2H5OH and C2H5OH, you are breaking the hydrogen bond. Remember, when you boil a covalently bonded substance, you're not breaking covalent bonds, but you're breaking intermolecular bonds. You evaporate water, again, you are breaking the hydrogen bond between them. You're not breaking covalent bond. When you dissolve bromine in water, then you're overcoming the London dispersion force here, and between water, you are breaking hydrogen bonds. So the only place you're breaking a covalent bond is when you're melting silica or quartz. That was number 17. Harshita, Stephen, hopefully you got, no, that was Harshita's question. Is the molar mass related to boiling point? Yes. For non-polar compounds, molar mass is an indication of how many electrons it has. In turn, how much will the electron cloud distortion be, which in turn impacts the boiling point. So yes, molar mass is related to boiling point for London dispersion force bound molecules that have intermolecular force as London dispersion force. Shravya, 25C be true or false? Oh, Shravya, I see what you're saying. So in 25C, you wouldn't get it because this is phase diagram based, which is phased out. Haha. So you will not be asked to do 25C, but you should know in terms of intermolecular forces, which is being broken, which is being formed. Ellen, are we going to be given the molecular formula for everything like benzene? Yes. And if I skip, because we used to do formulas first till the last year, so sometimes I forget that, then you can always ask for a formula. We haven't done naming yet, so you're not expected to know any formula. So if you are in need of knowing any formula, feel free to raise your hand and ask. You are welcome, Harshita. Any other questions on the blue packet? You're welcome, Alan. Very good question, Stephen. Yes, metallic bonding is considered both inter and intra, and metallic bonding comes in the next learning objective, Unit 6. But here is what I'll give you just a quick, brief overview of metallic bonding. So in metallic bonding, like aluminum foil, what happens inside aluminum foil, you know, aluminum has 3 valence electrons, right? So all of the electrons stay with aluminum except for its valence. So there's kind of an aluminum nucleus plus all the core electrons, but the 3 valence electrons break free and are given to the common space. They are called delocalized electrons. And bunch of this phenomena is happening all throughout. So each aluminum core's valence electrons are roaming in this free space, delocalized. Think of it as a community model of living, like their children playing, right? Whichever house they're playing next to, they go and get snacks from there. So if this electron, though originally it might have belonged to this atom, is close to this, it might be momentarily attracted by this. And then when this electron comes here, it might be attracted by another aluminum nucleus. So there is this electrostatic attraction between these delocalized electrons and the positively charged atoms. It's a wrong terminology, but that's how we say it, okay? And this force is electrostatic attraction. And this is governed by Coulomb's law. Again, Q1, Q2 over R squared. And the larger the cation's charge, because electron charge is always -1. The larger the cation's charge or the smaller the cation's radius, the stronger the metallic bond. So metallic bond strength can vary, but generally speaking, it is lesser than ionic bonds and it is stronger than hydrogen bonds. But metallic bond strength really varies. Some have very low melting boiling point and some have high melting boiling point. Harshita wants 25D, and 25D asks, iodine is more volatile than bromine. So you know, in iodine, and bromine, both of these are non-polar covalent compounds, right? They are 2 of the same kind. So what will be the intermolecular force? LDF. In LDF, you're looking for larger electron cloud, and iodine will have a larger electron cloud. So iodine will have stronger LDFs. Hence, iodine will have higher boiling point as compared to bromine. And they say iodine is more volatile. So this is true. No, this is false, because iodine will be less volatile. Volatile means weaker intermolecular forces so that they can go in the gas phase easier. Iodine will have stronger London dispersion forces, which will keep the molecules together and make it less volatile. What does it mean by RepCal in number 19? I swear that's a typo if it is RepCal. No, it's not RepCal, it's repeat. That is my handwriting, Stravia. So I meant to say this question is a repeat. It has been asked before, so you don't need to do this again. You guys are welcome, Stephen and Harshita. I'm going to spend a couple more minutes here, and then I'll move on to the practice quiz. So any last minute questions on the blue packet? Okay, now the practice quiz. Okay, any questions on practice quiz, guys? Those of you who have not taken the quiz, I suggest you pause this video here and leave the session. Go take your quiz like a quiz, timed about 30 minutes. One thing that I wanted to tell you all is the practice quiz and the real quiz will be a little different, because your real quiz will look like your practice quiz plus the formative assessment that you took the Friday before I left. Remember, there were a couple of handouts that had 3 or 4 questions. They were AP redesign questions. So I'm going to give you some of those kind of questions in addition to the practice quiz. So your real quiz will be longer, almost twice the length of the practice quiz. Please keep that in mind. Just wanted to let you know that. Alrighty, what questions on the practice quiz can I answer for you? Number 4. All right, Jocelyn. So they ask you in number 4, look at the graph below showing the deviation of ideal gas from the real behavior. Let me make this graph. Anybody who hasn't taken the practice quiz, please leave this video at this point. I'm going to do number 4, 5, 1. So can I start with 1? So I'm going in order 1, 4, 5, 6. Wow. Okay, number 1 has so number 1 has 1, 2, 3, 4, 5 balloons. Those of you who haven't taken, leave the video, come back to it. They are the same size. There are 5 balloons that are same size. They have CO2, they have O2, they have He, N2, and CH4. They say there are 5 different balloons filled with different gases at room temperature and pressure. So their temperature and pressure are the same. And if they are the same size, as a side, you can tell that their moles will be the same. Anyways, that's not what this question is about. This question says, which of the following gases is most likely to deviate from the ideal behavior? You know, the largest gases or the ones that have, so either they are larger so that their volume is non-negligible, or their intermolecular forces are non-negligible. And by both criteria, CO2 is that because its molar mass is 45 grams per mole, which is largest of any of these. So it'll have significant particle volume. It'll also have the strongest LDFs. All of them have LDFs. This will have strongest LDF because of the highest molar mass. So this will deviate the most. Number 4. Number 4 has a graph that shows ideal gas as a 0 line, okay, no deviation. And then you see that one of the gases going like that, one is going like that, and then there are 2 going like that. So a lot of gases are showing deviation on both sides of the pressure volume graph, and this is plotted against pressure. And it asks you, why are real gases behaving or deviating from the ideal behavior? And that is in this context. So if you look at this one, this is CO, and actually I didn't draw them right. This one needed to be the first one. So this goes here, this is CO. Then the next one is CH4, and then H2, and then HE. So if you look at the deviation is the greatest for CO, then so CO's molar mass is 12. You identify that all of these have London dispersion forces, right? There is no other force of attraction. And London dispersion forces are stronger with larger molar mass. So if you look at the molar mass, 12 plus 16, it's 28 grams. This is 16 grams. This is 2, and this is around 10, right? So CO will have the most deviation, followed by CH4, followed by H2 and HE. This is not NE, this is HE, so this is 4 grams. And the deviation is greatest for CO because of the highest molar mass, and it is deviating the most from The mass is where it's going with it. That is the question that's asking. Okay, Jocelyn. Then question number 5 is separation technique. And what you see is a column here. And what you see here, something being collected here. And what you noticed in the first one, in the color picture, it's very clear, is in the first one, you have like some molecule on top and another type of molecules here, right? And then you see some of these top molecules come like more to the bottom side, right? They are asking what separation technique is shown. And I think it is gel chromatography. As you're passing the solvent from top to bottom, you see that this component starts moving with the solvent. And what are the two different types of molecules representing? So this molecule probably is representing the gel that is used as the stationary phase, and the other molecule is representing one of the components of mixture. However, if you saw the other molecule as two components of the mixtures, then I can take that as well. Or if you saw it as stationary and mobile phase, I can take that as well. So that is number 5. Then number 6 is which of the solids is best conductor of electricity? So know that the best conductor of electricity is the one that either has a charged ion or free electrons that can carry current with them. So you're looking for charged ions with ability to move or bunch of electrons to carry this charge. So if you look at it, tungsten being a metal will have bunch of those free electrons to carry the electricity. That's why metals are good conductors of electricity. So answer is A. And because C, sodium chloride, is in solid form, it's not a good conductor. If it was aqueous or liquid NaCl, where you just melted NaCl, then yes, that will become a good conductor of electricity. For number 7, how do we identify if things like SiO2 just covalent? You have to just memorize. I am sorry, Ethan, for skipping your question earlier. The covalent network compounds, you have to just memorize. There is no other way to identify. There is one thing common, that they are all around carbon or metalloid group there, but you have to just memorize. Germanium, Ge, Si, SiO2, graphite, which is carbon, diamond, which is carbon, allotropes, they're just made up of carbon but have different properties. This is the list of covalent network compounds. You just have to memorize them. This is the list, common list, Ethan. You're welcome. I think that's pretty much all the questions in here. This is a shorter practice quiz, guys. I'm again reminding you, the actual quiz will be a combination of the formative assessment plus the practice quiz. It will be longer than the practice quiz. All right, I think that is it, elements, unless you have any last minute question. 1 more minute. All right, elements, that is it. You got it. You'll be fine tomorrow. I'll see you bright and early tomorrow. Have a good Sunday. Bye. Thank you, everybody. Bye-bye. Thank you so much, guys. Bye. Oh, shucks. Oh no, I had a piece of crumb on my face all this while. Finished.